Hello, everyone. In our earlier video, we introduced our new discovery. We found the smallest constant of physics. It is the smallest value of the product of space, time, and energy. In this video, we will, based on the earlier discovery, we do some calculation, then we get some very interesting development of our theory or research. This video we will talk about the cosmic evolution. This cosmic evolution is very closely related to the physical properties of the elementary particles. So let's begin. In our earlier video, we talked about our new discovery, the smallest physical constant. So right now we do a little bit review. The smallest constant, we call it is K naught. It's space, time, quantum of action. It is STQA. Because this number is very, very small, so we introduce hypothesis. This is called STQA hypothesis. We can see every particle or every physical system, their energy, their space interval, and the time interval, the three quantity multiplied together should be the integer times of K naught. This is the STQA hypothesis. Then, based on this formula, we can prove that every element, every quantity, for example, the energy and the space and the time, should all the function of n. N is a positive integer. Then we can get these three formula: the energy, space, and the time. Then we can see we get four new parameters. It is A, B, D, and N. N is the positive integer. The A, B, and D all plus together, it should be 1. It's based on this formula. Then we can deduce, combine with the fractal geometry, the dE, dx, d tau is the fractal dimension of energy, space, and time of all the particles of physical system. Then in our earlier video, or in our published article, we calculated all the parameters, the A, B, D, and N for every elementary particles. Then we get a table in earlier video. Based on that data, we can do more calculation. This is the content we want to talk in this video. Based on the parameters we calculated for the A, B, D, and N for every particle, we can put all the numbers in this map. In this map, here is the logarithm of the n, because the n, the value is very big. So we use the logarithm of n. And in this value, we directly use the A, B, and D from the table. Then we draw this map. In this map, we can divide all the particles into two categories. One category is the heavy particles. For example, the proton, the neutron is the heavy particles. And another category is the lepton. For example, the electron, the neutrino, and so on. Then based on this map, we can see all the points we draw, we take the value log n and A, B, and D. Then we draw the point. We can see the point is almost in a line, a strict line. For example, for the heavy particles, this line is the A, and the lepton, this line is for the leptons A, and this line is the heavy particles B. This line is the heavy particles D, and this line is the heavy leptons D, and this line is very special. It's for all the particles B. That means every particle, no matter is lepton or heavy particle, their B is all the same, is in this line. Then we can deduce for the heavy particles, we get these three formula. The lepton, we get these three formula based on this map. Then we, based on the 6 formulas in the lepton and heavy particles, we do more calculation. Then we can find for the heavy particles, we can get a heaviest mass, and for the lepton, we can get a lightest mass based on the 6 formulas. So we don't want to go through too much mass calculation. So we just have the result. Through this calculation, for heavy particles, we can get this formula. Then do the calculation, we can get this heaviest mass. For the lepton, we do similar calculation. The formula is the form is similar, but the data, the value is different for the heavy particles and the lepton. Then we get these 2 value. The heaviest mass and the lightest mass. That means for possibly exist elementary particle, we get an upper limit for the mass and the lower limit for the mass. These 2 limits from the currently we found the elementary particles, we if we see their mass, all the mass is between this value and this value. We can see every possibly existing elementary particle, their mass is they cannot beyond the heaviest mass, and also they cannot below the lightest mass. So this is a prediction from our research. So we will waiting for the test from the experimental test. And we get another interesting result. This for the motion parameters of a particle. Because every particle, their properties depends on the STQA's content included in the particles. Based on the number of STQA's included in the particles, it is the n or log n. Then we can calculate the particles A, B, and D. So every particle we talk about their properties, we just use 4 parameters. It's A, B, and D, and N. Then because for every A, B, D, and the formula in the upper in the lepton and heavy particles, we get their formula is a linear formula. So we just write down the formula in general is for A, B, and D. For every particles, we use these three formulas. Then we can calculate every particle. They have a intrinsic motion acceleration when we use Q. Stand for the acceleration. Then they have a curvature in the space and the time. We use rho represent the curvature. And the force. The force we can see is a curved space and time exert to the particle. You get a force. Then we put the value for example, the electron. We put the value into this formula. Then we can calculate the electron, the acceleration, the curvature, curvature radius, and the force. And for the proton, we can get these values. For the heaviest particle, we can get these values. So this is very interesting. You can see the lighter particle, for example, electron, their curvature, the curvature radius is big, and the heavy particle, the curvature heavy particle curvature radius is smaller. That means that the heavy particle, their curve, the curve in the space and time is very big. As the lighter particle, the curve in the space time is smaller. So this is the interesting result. Then we talk about the cosmic evolution. Based on the formula in the map, we can see that all the particles, their B is all the same. So we just see the B, the relationship between D and B and log n. Relationship between B and log n is not related to any kind of particles. In general, we can see every particle, every physical system, their B, we can use the same formula. Then we take this formula into the x equal x naught n to the power of b. Then we get these functions. We can see these functions is they have a minima or maxima value. For this function, they have maxima value. Then we can calculate the maxima n is 10 to the power of 183. This value is very interesting. We can recall in our earlier video, we already calculated the n value for our universe in currently universe. Their total n value is almost 10 to the power of 182. So here we get 10 to the 183. So that means this n value for the whole universe should be the same. So right now we just take the value is 10 to the power of 183 as the total n for our universe. And for our universe, this n should be a constant. It's no change, no matter in the beginning, right now, or in the end. Then we can calculate the value of B and also the dB. dB is the fractal dimension of space. And we also calculate the space, the maxima value, because our universe is expansion. So it will reach a maxima space length and also a maxima time. For the beginning, for the Big Bang, our universe, based on our calculation, we already see the total value of n, our universe. We take this value. Then, in the beginning, in the Big Bang studies, that means the total this much STQAs, we put them into this extremely small space-time range without the x0 and the tau0, based on the STQA survey. Then we just take in the Big Bang studies, we let the x equals 2 times x0 and the tau similar. Then based on STQA hypothesis, we can use these formulas to calculate in the Big Bang studies. We can get the A, B, and the D, and also the energy E. We can see the A also almost is 1. The B and the D is the same. They are all very, very small. It's 1 over the 607.9. It's a very small value. And the energy is very big. It's 10 to the 200 erg. Right now, we just take a review of our current universe. We already calculated the current universe, all the parameters, based on the current universe, the age, the energy, Then we calculate the current universe, the n is almost 10 to the point of 182, this value. And also we calculate the dimension, the fractal dimension for our current universe is almost all the three. We already talked about in our earlier video. So right now we get three group of B and tau values. One is in the Big Bang standards. One group is in the Big Bang standards, and one group is in the current universe, and another one is in the maxima expansion standards. Then we use based on three group of B and tau values, we can draw a curve for our whole universe. In this map, we use log tau and log B as a coordinate to draw a map. This map, we can see three special points. One is the Big Bang point, and another one is the point. This represents the universe right now. And another one is the point B. There is the maxima expansion value. And this one is point A. In this point, we can see the how universe their B or their B value is getting smaller and smaller. No, the B value is getting bigger and bigger as time passed on. We know the fractal dimension is the inverse of B. That means the fractal dimension for our universe is getting smaller and smaller as the time passed on. In the beginning, the fractal dimension is 6.607.9. It's very, very big. Right now, it's 3. Right now, the fractal dimension of space is 3. And in point A, the fractal dimension will become to 2. And in the point B, will reach the smallest value. It's 1.83, 86, something like that. So this our universe evolution curve. Based on this evolution, we can see the all the so for the space dimension, our universe is getting smaller and smaller. Right now, it's 3. This is very interesting result. If the space dimension is 3, that's no problem. We just live in this situation. But if our theory is correct, our all our result is based on the calculation. If the calculation is all reliable, is correct, so that means we get the conclusion. The space dimension is getting smaller and smaller. This should be cost our all attention in that, because this will cause many very serious problems. Because the dimension, if the dimension smaller than 3, what happens for our human beings, the living? For example, if in this situation, the dimension becomes 2, so in 2-dimension space, so how can we live? So we need to take this very seriously right now. And another problem is because our theory, we get the all the dimension is fractal dimension based on the similar self-similar set in the fractal dimension. We know the self-similar system, they have a similar structure in every size scale. So if the space, the fractal dimension get smaller and smaller, so that means in space or time, we will get some void or holes in every size scales in our universe. So that will be cause, I think, will be cause some very important influence in our living thing, in our living. So we just get this interesting result, but I think this is not interesting. Is we should take a very serious care about this problem, because our universe, the dimension will get smaller and smaller. So this we should do more and more research on that. So this is our recently the new result we get. And if you want to see our published articles, you can go through through this link to take a look. Okay, our today's video will stop here. If we get more interesting result in the future, we will make more another video. Okay, thank you very much for your watch, and see you next time.